Welcome to ePadasala lecture series in computer science. Today we are going to discuss about the divide and conquer, and we are trying to apply that for certain computational problems like the closest pair problem and convex hull. The objectives of today's modules are going to be like this: to understand the concept of the closest pair problem. Already this problem was discussed along with the brute force strategy. So now we are going to apply the divide and conquer strategy for the closest pair problem. To know about the convex hull, again this problem was referred as part of the brute force strategy. So today we are going to apply the divide and conquer strategy for finding the convex hull. There are two standard divide and conquer solutions are available. One is called the quick hull algorithm and another is called the merge hull algorithms. So let me recollect the closest pair problem that was discussed as part of the brute force strategy. So here we are given a set of points. The points can represent the cities, or it can be a transistor in a circuit board, or it can be the computers in a network, and the objective of this problem is to find the closest pair of points. So that means we have to return 2 points that are closest to each other. Formally the problem statement can be given like this. So n points are given in 2-dimensional space. So what we have to do is we have to find the distance between 2 points where it is minimum. So that means if P and Q are points that belongs to the set of n points, and we have to return the points P and Q for which the distance is going to be the minimum. So the solution is very simple. In brute force strategy we have seen how to solve this problem. So in brute force strategy we applied the brute force to find the distance between any point and any other point, and finally we found the points that are close to each other and we returned those points. That was a solution outline as part of the brute force strategy. So how to find the closest one? So again you can recollect that we solve this problem by means of the distance measure, and lots of distance measures are available like Euclidean distance, Manhattan distance, city block distance, etc. And this is the formula for finding the Euclidean distance. Given 2 points of the coordinate positions, this is the formula to compute the Euclidean distance. So you can recollect in the earlier module we discussed that the Euclidean can be a fraction, and sometimes it takes a lot of time because it involves finding the squares as well as the square root 2. So in that case we can go for some sort of an approximation. For illustrations let us take the Euclidean distance, even though it is computationally larger compared to the other distance measures. And also you can recollect that the distance between 2 points A and B is equal to the distance between B and J. So this is called the symmetry property, and the distance between a point and the very same point is going to be 0. It is called the constancy of the self similarity, and already we have stated that the distance is always going to be a positive number. So that means the distance between 2 points A and B is going to be greater than or equal to 0, and this is called the triangular inequality. That means you can see very well that the distance between A and C and the distance between C and B is always going to be greater than or equal to the distance between A and B. In other words, if these properties are satisfied, then we can call the distance as a metric measure. Otherwise it is not so. So once we defined that, probably you can recollect we wrote a informal algorithm like this. So, where we have taken 2 points I and j, and we put a constraint that the points I and j are distinct. So, under that circumstances we have computed the distance. So, every time we are computing the distance, we are keeping track of the minimum distance also. So, whenever the distance is going to be the less than the minimum distance, then the minimum distance is updated, and finally once all the points are reviewed, finally we get the minimum distance between 2 points I and j, and that is being written as the minimum distance for the points I and j. This is the informal algorithm that we discussed as part of that. So, what is the complexity analysis of this particular algorithm? You can see very well. So, we have a loop for 2 variables. So, under those circumstances, this is going to be the constant amount of effort that is required for finding the square and the square root. By simplifying this, you can come to a conclusion that this is going to be the order of n square algorithm. In other words, the brute force algorithm for finding the closest pair is going to be what is a order of n square. So, now the challenge is very simple. Is it possible to improve the performance of the algorithm? In other words, is it possible to reduce the complexity from the order of n square? So, for that reason only we are going to go for the divide and conquer strategy. So, recollect that in divide and conquer strategy we have taken a problem, we try to divide that into number of sub problems. So, we have seen that the sub problems are similar to the original problems, but smaller in size. Then we solved all the sub problems, and finally, when we combine the solutions of the sub problems, we are getting the solution of the global problem. The same strategy can be applied for finding the solution for the closest pair problem. You can see very well informally the steps are like this. So, when n is very small, we are trying to solve the problem using the brute force, and when n is very large, we are trying to divide the point set into roughly equal parts A as well as B. And now we have 2 subsets. We are trying to find the closest pair in first set A and second set B. Then we are trying to find the closest pair of points where one point is on one set and another point is on another set. Finally, once all these closest pairs are computed, then we are finding the pair for which the distance is going to be the minimum. So, you can see very well this problem is what the divide and conquer strategy is all about. Fine, as an illustrations, let us take the set of points. So, as I said earlier, these points can be the cities of any country, it can be a transistor in a circuit board, or it can be the computers in a network. So, now the point is like this. Given a set of points like this, can you say which is the closest point? So, you can see very well we are trying to apply the divide and conquer strategy. The first step is the division. So, now what we are going to do is we are going to divide this set into subsets like this. So, that means we are going to divide such that the region A have coordinate x coordinates less than or equal to the points that are present in the set B. So, that means you can see very well this is the median line that is going to split this set of points into 2 subsets. So, once we have 2 subsets, so you can recollect how our strategy is going to be. So, we are going to find the closest pair in set A, and we are going to find the closest pair in set B, and then we are going to find the closest pair of points where one point is in region A and another point is in region B. So, you can see very well, now you can find the closest pair of set A. So, let us assume that D1 is going to be the distance between the points that are closest in the set A. So, this is how it goes for the other set. In other set B, so you can find the closest points for which the distance be D2. So, now you can see very well the minimum distance is what our objective is. Therefore, the minimum distance is going to be the minimum of D1 and D2. So, that means let us call this as the distance D, but one case is left out, that is, there is a possibility that the closest points can be across the set, where one point can be in set A and another point can be in set B. So, that means our answer is not complete until that is obtained. Fine. So, for that what we are going to do is we are trying to find the portion across this line where that distance between points across the regions needs to be computed. In other words, let us assume that D1 is going to be the minimum distance. If that is the case, then only that minimum distance across this line needs to be examined, and there is no point in finding the distance between, let us say, this point and this point. It is of no use at all. So, what we are trying to do is we are trying to find the minimum D, and then we are trying to create a border around this line, so that the third case can be restricted to this particular portions. So, now you can see very well this creates the region. In fact, two regions are created where the third case needs to be applied. Let us call this as region A and region B. So, now this region needs to be explored for the third case, right. Fine. So, let us take this particular point. Fine. So, let us call this point as Q. So, as per our logic, this exists in region A. So, according to the third case, the corresponding closest happens to be on this side, that is in region B. So, this is where we need to apply some sort of a thinking. So, this point, this corresponding point for Q cannot happen beyond this particular point, because this is where the minimum distance D is all about. In other words, you can see very well the corresponding point for Q should exist only in this particular region, because if the corresponding point is outside this region, then the distance will be more than what already we have computed as the minimum distance D. Therefore, now we can come to a conclusion that for finding the correspondence, only this region needs to be analyzed. In other words, you can see very well. So, this region only we have to check 6 points and not more than that. So, that means, now you can see very well the distance computation between the point Q should be done only with what you say these 6 points. In other words, now you can see very well the problem is now reduced to just 6 comparisons. So, this is a linear time. Therefore, we can come to a conclusion that suddenly the algorithm complexity is reduced, because we need to compute the distance between Q and only these 6 points. Okay. So, this is the maximum comparisons that is required. So, therefore, this fastens the process. So, now you can see very well how our algorithm is going to be. If the number of points are going to be very small, So, we are going to solve that using the brute force approach itself. Otherwise, we are going to divide the problem into sub problems, then we are going to solve the sub problems in a recursive manner, and then finally, we are going to combine the solutions of these sub problems. So, we will apply this strategy to this particular problem. So, we are given a set of n points, and this is what our objective is going to be. So, as I said earlier, what we are going to do is we are going to arrange this by sorted order. So, if S consists of only points written infinity as a distance, otherwise we are finding the median line. So, and then we are trying to divide this set into two subsets with equal size, that is SL and SR. So, then we recursively apply. So, this is what the conquering strategy is all about. So, apply step 2 and step 3, so that we can find the closest pair of the set SL and SR. So, let DL denote the distance between the closest pair in SL, and if DR is going to be the distance between the closest pair in SR, then you can say that the minimum distance is going to be the minimum of DL and DR. So, as said in the numerical example, once you find the distance, so what we are trying to do is we are trying to find the grid, and the grid size is going to be L minus D. So, that means now this is the half slab, and once we have this L minus D and L plus D. So, now the third case becomes simple. That means we have to find the distance between the point and all other points of this particular grid, and again you can see very well only the 6 points needs to be computed for finding this. So, what is the running time of this algorithm? So, the division is very simple. So, it is just takes only the constant time, and once you compute all the distance and combining takes order of log n. In other words, the recurrence equation is going to be like this. If n is going to be less than or equal to 3, then it is going to be n, or otherwise this is what the recurrence equation is all about. Find the total time is not more than what is a order of n log square n. So, this is definitely better than the brute force, but still lots of improvements can be done, but definitely this is better compared to the brute force approach. So, this is the kind of algorithm that is used for the closest pair. So, now we will just extend our idea for solving the problem of convex hull. Again, this problem was solved as part of our brute force strategy. So, you can recollect how we solve this problem in brute force strategy. So, let S be the set of points. So, if we assume that the points are supposed to be the pegs, then we can assume that the convex hull is the shape of the rubber band that is stretched around those pegs. In formal manner, we can say that the convex hull is nothing but the smallest convex polygon that contains all the points of S. So, this is the example of convex hull. So, you can see very well these are the points. In convex hull, what we have to do is we have to construct the smallest polygon such that all the points will be covered, and that should be the closest one. So, you can see very well this is the convex hull that can be constructed for this set of points. We talked about why convex hull is a very important concept in computer science. Lots of applications of convex hull is there. So, one application is it is useful to find what you say the collision of the robots in the field of robotics as well as in games design. So, in brute force strategy we have seen that the problem of convex hull is reduced to finding the extreme points. So, extreme point is a point that is not the middle point of any line segment with n points in the set. So, we have seen that extreme points form the vertex of the convex polygon, and any points that are within that set is called the interim point that can be excluded. So, you can see very well how we solved the problem in brute force strategy. So, in brute force strategy we have taken 2 points P I and P j, and we have constructed the line segment, and what we have said is all the other points should exist on one side of the line in order to qualify that these 2 points form the vertices of the convex hull. And if there is any point that lies on both the sides, then we can come to a conclusion that P I and P j are not going to be the extremal points. So, we try to apply this logic for all the points. So, the brute force approach algorithm is captured in this particular slide. So, you can see very well you have taken points P and Q, and you try to construct a line, and then you check the points, and you can see that all these points are on one side of the line. Therefore, you can come to a conclusion that P and Q are going to be the vertices of this convex hull. So, that means you can see very well that P and Q form the important point in the construction of the convex hull. So, these points you can see very well are called the extremal points, because these forms the vertex of the convex hull. These points are called the interim point. So, these points are not important because these are no way what is a helps in the construction of convex hull and can be eliminated. So, the logic is very simple now. So, we have to apply the divide and conquer strategy for finding the convex hull. So, we want to improve the performance of the brute force technique. So, we want to reduce the complexity. So, lots of efforts have been made. One such effort was made by the person called Propreta and Shamos in 1985. So, to construct the convex hull, and the algorithm is named as the quick hull algorithm because of its resemblance to the quicksort algorithms. So, the logic is very simple. We identify the points A and B. What we are trying to do is we are trying to check whether these points are going to be what we say the extreme points or not. So, for that to happen, what we are trying to do is we are trying to find the farthest point C from the line A and B. So, now we are trying to construct some sort of a triangle with these points, and then we are going to check whether the points are falling within this triangle. Otherwise, we are coming to a conclusion that this is not the convex hull. This is the illustration of this particular idea. So, you can see very well there are lots of points are there. The problem is to find the convex hull of these points. So, we are taking two what is a points that are distant from each other. So, A and B. So, now we are constructing a line between A and B, and we are trying to find the farthest point for this particular line A and B. So, let us assume that this is the farthest point of this particular line, means now we are connecting A and C and B and D, so that we have some sort of a triangle. So, you can notice the similarity between this algorithm and the quicksort. In quicksort also, what you are trying to do is you are trying to partition the list into two lists by choosing a pivotal element, so that the list will have more or less similar points. The same logic is being used for the construction of this particular triangle. So, once we have this triangle, so what we have to do is we have to check whether these points fall within or outside the triangle. If all the points fall within the triangle, then we can come to a conclusion that this is going to be the vertex of the convex hull, otherwise it is not. This is what the idea is all about. So, you can see very well the set of points are tried to divide into two sets by P1 and Pn. So, line is constructed. So, a point P max is obtained, the triangle is formed. So, you can see very well all these points are very important and these points are not going to be what you say important at all. So, this is what the informal algorithm is all about. So, we are taking a set and we are finding points P1 and Pn. So, we are trying to what you say find P max, then we are constructing what you say the triangle, then you can see very well we are getting triangle and the result is going to be the quick hull P1 P max A, which is concatenated with quick hull P max Pn and B. So, this is the elaboration of the informal algorithms. So, you can see very well the points are first sorted based on the x coordinates. First point is P1 and Pn, so that these two form the points for which the distance is going to be the maximum. So, as I said earlier, we are constructing a line segment between P1 and P1, so that the set S is divided into two subsets, S left and S right, and for S left what we are trying to do is we are trying to find P max. So, what we are trying to do is once this P max is obtained, we are trying to form the triangle. Ignore all the points inside the triangle P1, P max, Pn, and the left convex hull is going to be the union of P1 and S11, and S11 is nothing but the set that is created by the division of S left by this particular line. So, the left convex hull is going to be P1 union S11 union P max, and similarly the right convex hull is formed. Then finally, by combining this left and right convex hull, we are getting the final convex hull. What is the complexity analysis of this algorithm? The complexity analysis of this algorithm is exactly similar to the quicksort. You can recollect that the worst case analysis of quicksort is order of n square, and for average and best case it is going to be order of n log n. In other words, this algorithm complexity analysis is also exactly similar to the quicksort algorithms. The same problem can be approached in a different angle. It is called the merge hull. So, the logic is very simple. Again, we are going to use the divide and conquer strategy. We are going to divide the set into two subsets, and we are going to construct the convex hull for the two subsets, and then we are trying to merge everything to get the final convex hull of the given problem. You can recollect the similarity of this with merge sort. So, that is the reason why we are calling this as the merge hull. So, we are trying to divide the problem into two subsets of n by 2 each. You construct convex hull for both the things, then we are trying to combine everything. So, this is what the hull is going to be. So, we are trying to find the upper tangent and the lower tangent, and once we have this, then we are going to merge everything to get the final convex hull. This is what the algorithm is going to be. So, we are taking the set S, then we are trying to divide this into two subsets, S left and S right, just like our merge sort. Once the sets are formed, then we are forming the convex hull, then we are trying to find the lower and upper tangent. Then once we have this, then we are going to merge the left and upper convex hulls. This is what it is going to be. This is one convex hull, this is another convex hull, both corresponds to the points of two different sets. Now, I am trying to find the upper tangent and lower tangent, and once these tangents are obtained, then we can eliminate all the things so that it becomes the final convex hull. How to find that? Fine, you can see very well, we can trace this DE and F, and you can see very well the angle is going to be like this. Therefore, F is not part of F. So, F can be bypassed and E and G can be what is connected. So, using this particular logic, we can form the hull of both the left set and right set, and once we have that, fine, we can merge everything. What is the complexity analysis of that? The complexity analysis of that is going to be the order of n log n, because the complexity analysis is going to be exactly similar to the merge sort. In summary, we can come to a conclusion that brute force approach is applicable but inefficient, but divide and conquer is very effective, and closest pair problem and convex hull problems are very important problems in computational geometry, and we can conclude that divide and conquer is very effective for solving the closest pair problem as well as the convex hull problems. These are the references. So, with this thing we have come to the end of this particular module. Next module we will discuss some more applications of divide and conquer strategy. Thank you very much.